Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 3 on the unit circle. Now, you've never probably seen the unit circle or really what we're going to do today, and it's going to be a little messy. I'm not going to lie to you, okay? There's going to be square roots flying left and right. Pi is going to make an appearance many times, and it's really important that you've really seen both Lesson 1, when we talked about rotations and angle terminology, and Lesson 2, when we talked about the radian angle measurement system. Anyhow, hopefully you have seen those two videos or you've gone through those two lessons with your teachers, because now let's talk about the unit circle. To extend trigonometry to non-acute angles, we will use a very special circle known as the unit circle. This is a circle that has its center located at the origin and has a radius equal to 1 unit, whatever that 1 is. 1 foot, 1 inch, 1 mile, it doesn't matter. 1 unit. Hence the name, the unit circle. Now again, this is important. Back when we did trigonometry in geometry, all we ever did was find the sine, the cosine, and the tangent of angles between 0 and 90 degrees. But now we want to be able to find those trigonometric functions for angles like 120 degrees, 240 degrees, negative 330 degrees, pi over 2 radians, 2 pi over 3 radians, etc. All right? And this unit circle, strangely enough, is going to be the key to doing that. So let's just begin with a little bit of review. Exercise number 1. From our work with equations of circles, which of the following would represent the equation of the unit circle? Now, we actually kind of looked at the equations of circles earlier in this course when we solved linear quadratic systems. So take a look at these 4 choices and see which one you think is the equation of the unit circle. All right, well, I'm hoping that you chose choice 3. Now, I want to make sure that not only you chose choice 3, but you understand why that's the equation. Now, one thing at a very base level, the equation of any curve, whether it's a parabola, right, a circle, a line, an exponential curve, it doesn't matter, right, is that it's an equation that is true for every xy coordinate pair that lies on that curve, all right? So what I'm saying is that this is the equation of this, because if I took any xy pair that lied on here, whether it was a nice xy pair like 1, 0, 0, 1, or whatever, and I substituted it into this equation, it would make it true. Now here's why it makes it true, right? If that was supposed to do something. There it is. All right. If I actually took a point on this circle and I called it x, y, good choice, right? Then what I could do is I could drop a vertical line segment to the x-axis and draw in this right triangle. Now what I would know about that right triangle was that its hypotenuse would be equal to 1 unit because this is the unit circle, so the radius anywhere is 1 unit. But the cool thing is, of course, that this distance simply is the x-coordinate. This distance simply is the y-coordinate, and so I could relate the value of x, the value of y, and the number 1 using the Pythagorean theorem, right? Specifically, I could say a squared plus b squared is equal to c squared, where a is x, y is b, and c is 1. And 1 squared is, of course, 1. All right? Now that's important. Every point that lies on the unit circle, if I take its x-coordinate and I square it, and I take its y-coordinate and I square it, I will always, when I add those two together, equal 1. Always. Now, let's keep going. And let's talk about some special right triangles. Now, you saw these special right triangles back in geometry, but at least in our geometry course, we worked on them for a total of 1 class period. You may have worked on them a little bit more depending on what geometry class you took. We will now want to produce some of the coordinate points that lie on the unit circle through the use of the Pythagorean theorem. Given what I just looked at, that probably makes some sense. The next 2 exercises will illustrate the important right triangles we will need. Exercise number 2. Consider the right triangle shown whose hypotenuse is equal to 1 and whose angles are both equal to 45 degrees. Since this is an isosceles right triangle, the 2 equal sides are labeled x. Solve for x and place your answer in simplest radical form. All right, well, what I'd like you to do is I'd like you to try to solve for x using the Pythagorean theorem. It's going to involve radicals, okay? See how far you can get, and then we're going to go through it. Pause the video now and go ahead and do that. Now again, I kind of want you to picture, as we work in both exercise 2 and exercise 3, I really want you to picture these triangles as being one of these. Okay, and what we're really finding when we find that length will be the x-coordinate of the coordinate pair, and this length we're finding the y-coordinate of the coordinate pair. Now in that first particular problem, they're the same because this is an isosceles right triangle, also known as the 45-45 right triangle. Here we go, right? So I'm going to have x squared plus x squared is equal to 1 squared. So that's going to be 2x squared is equal to 1. Which means x squared is going to be 1/2, which means x is going to be the square root of 1/2. Now, if you got that far, it's awesome. And I kind of wish we could just leave it like that. I really actually do, because that's a lovely answer, the square root of 1/2. Unfortunately, most of the time there's some extra manipulation that's done to write this in, quote, simplest form. Now, we're going to get this in a different form, and if you disagree that it's simpler than this, then I will totally agree with your disagreement, all right? Whatever that means. Anyway, so we can take this a little bit farther, and we can say this is the square root of 1 divided by the square root of 2. The square root of 1 is just 1, so we get 1 divided by the square root of 2. Now, if you couldn't leave it like this, I wish you could leave it like that, but yet again, you probably can't leave it like that because there's a radical in the denominator, and we don't like that for some inexplicable reason that we're not going to go into right now. Now, back in both geometry and in Algebra 1, you learned how to do something called rationalizing the denominator. That means getting rid of the square root of 2 there. Historically speaking, we don't like square roots in the denominator. So what we do is we multiply by square root of 2 over square root of 2. That gives me a square root of 2 in the numerator, because 1 times square root of 2 is square root of 2. And square root of 2 times square root of 2 is 2. So we have square root of 2 over 2, and that is ultimately how we're going to leave it. Now again, that is equivalent to the square root of 1/2. It's also equivalent to 1 divided by the square root of 2. Either one of those I would completely take if I were a math teacher, but what generally is agreed upon as the simplest radical form is the square root of 2 divided by 2. Now let's take a look at a 30-60 right triangle. Exercise number 3. Consider the 30-60 right triangle shown whose hypotenuse is equal to 1 again. Recall from geometry that this triangle is half of an equilateral triangle. What is the length, letter A, what is the length of the shorter side of this right triangle? So no Pythagorean theorem involved at all. What would be the length of that shorter side? And the key is to remember that this is half of an equilateral triangle where all 3 sides are of equal length. Pause the video now and see if you can tell me what the length of that side is. Well, it might help if we draw in the other half of the equilateral triangle. And of course, since it's an equilateral triangle, that would have to be 1, this would have to be 1, this would have to be 1, and therefore the shorter side is 1/2. I don't need any Pythagorean theorem to figure that one out. Now that is the side that is across from the 30-degree angle in a 30-60 degree right triangle, or it's adjacent to the 60-degree angle, and that's going to become important in just a few minutes. But let's take a look at letter B. Using the Pythagorean theorem, find the length of the longer side in simplest radical form. And again, remember why we're doing this. We want to be thinking about that 1/2 as sort of an x-coordinate, and whatever that height is as being a y-coordinate of a point that lies on the unit circle whose radius is equal to 1. So what I'd like you to do is, I don't know, call it y, maybe. See if you can figure out, using the Pythagorean theorem, the value of y in simplest radical form. Pause the video now and take a few minutes to do that. All right, well, let's do it. This one's kind of similar to that previous problem that we did. We're going to have 1/2 squared plus y squared is equal to 1 squared. 1/2 squared is 1/4. plus y squared is equal to 1. That means if I subtract a 1/4 from both sides, y squared will be equal to 3/4. So I'll now take the square root of both sides. So y is the square root of 3/4. And again, just like before, I wish I could leave it like that. I really do. All right? But that is not considered simplest radical form. I'm going to now write this as the square root of 3 divided by the square root of 4. There's nothing I can do with the square root of 3. The best I can do is leave it as square root of 3. But I can make the square root of 4 into 2. And so the height there is going to be square root of 3 over 2. And let's draw, well, actually, let me leave the y on there, but let me write it as square root of 3 over 2. So when we have a 30-60 right triangle, moral of the story, when we have a 30-60 right triangle whose hypotenuse is equal to 1, never forget that, then the shorter side is going to be 1/2, and the longer side is going to be, or I should say legs. The shorter leg is going to be 1/2, the one that's across from the 30-degree angle, and the longer side, the one that's across from the 60-degree angle, is going to be root 3 divided by 2. Okay, so now we're going to come up with the most complicated diagram you will ever draw in mathematics, and I mean ever, filling out the unit circle. Now, to begin with, I want to be very clear about this. There are an infinite number of points on the unit circle, an infinite number, as there are on any continuous curve. Some of these, we can now find the exact coordinates of based on our special right triangles, and also just based on common sense, okay? So, let's take a look at exercise number 4. The diagram below represents the unit circle. Using what we learned in the last 2 exercises and our study of radian measure, do the following. Letter A. For the 5 angles labeled, state the equivalent radian angle measure and state the coordinates at each point. All right, so let's take care of the first thing first. State the equivalent radian angle measure. This is where you have to have seen our lesson on radian angles or you're just going to be completely lost. Now, one thing that we talked about in our radian measurement is that 0 degrees is the same as 0 radians. The other one that was exceptionally important was 90 degrees. 90 degrees was equal to pi over 2 radians. Okay? But on the homework, I also asked you to really get good and memorize a few other important ones, specifically 30 degrees, 45 degrees, and 60 degrees. Now, 45 degrees is half of 90 degrees, and half of a half is a quarter. So 45 degrees is pi over 4 radians. Okay. 30 degrees, this is going to probably bend your mind, 30 degrees is 1/3 of 90, and 1/3 of 1/2 is 1/6. 30 degrees is pi over 6 radians. Now, 60 degrees is twice 30 degrees, so it must be twice pi over 6, and if I have 2/6, then I have 1/3. Now I want to be very clear again. Those are not the coordinate pairs. Those are simply the angles measured in radians instead of being measured in degrees. Now, whenever we measure angles in radians, we typically don't actually have the rad there or radians there, but I'm going to leave them there for now. But eventually, when you see the diagram fully written out of the unit circle, you'll notice I won't have rad written there. It will simply be 0 degrees equals 0, 30 degrees equals pi over 6, 45 degrees equals pi over 4, 60 degrees equals pi over 3, and 90 degrees equals pi over 2. Those angles you want to have memorized in terms of the degrees and the radians. Now let's talk about coordinate pairs, okay? And let's start with the 2 really easy ones, okay? At 0 degrees, we're sitting right here. Now never forget, we're talking about a radius equal to 1, and so its coordinate pair is a piece of cake. It's 1, 0. And actually, maybe I'll write the coordinate pairs in red just to kind of contrast them with the actual angles. So that's not 0, 1. That's going to be 1, 0. So at 0 degrees, right, we are at the coordinate point 1, 0. This is where the terminal ray crosses the unit circle. The other one that's very easy is when we're at the top of the circle at 90 degrees or pi over 2 radians. That's going to be the coordinate pair 0, 1. All right. Now, how about at 45 degrees? Well, at 45 degrees, right, what we've got is we've got that 45, 45 right triangle that we looked at in exercise number 1. Okay? And therefore, it's got the coordinate pair square root of 2 over 2, comma, square root of 2 over 2. That is its coordinate pair. I know, it's an ugly coordinate pair, but it's a coordinate pair. And believe it or not, if you squared that number and you squared that number and you added them together, you would get the number 1. X squared plus y squared is equal to 1 squared. Okay, so now let's talk about these two, the 30 degrees and the 60 degrees. And I'm going to just, for the time being, well, apparently I'm just going to move that triangle. I'm going to do this. Now here, when I look at the 30 degrees, this is my 30-60 right triangle, where this is 30 and this is 60. Okay, because that's a 30-degree angle. Now remember, in our 30-60 right triangle, with a hypotenuse equal to 1, the shorter side was 1/2, and the longer side was square root of 3 over 2. So this is square root of 3 over 2. I wouldn't mark these things on right now because otherwise your diagram is going to get very, very ugly. And that is 1/2. And therefore our coordinate pair for 30 degrees is going to be the square root of 3 over 2, comma 1/2. Simple enough. Ugly, but simple enough. Now on the other hand, that's just going to keep happening. On the other hand, if I go to this particular triangle, this is also a 60-30 right triangle. But what you can probably tell is that these coordinates have now been flipped. In other words, this is my shorter side at 1/2. This is my longer side at root 3 divided by 2. And so my coordinate pair here is 1/2, comma, root 3 over 2. And believe it or not, that's pretty much the heavy lifting. There's a lot more of this diagram to fill out because we still have to do quadrants 2, 3, and 4. But we've now done the hard part. Everything else we're going to be able to pretty much get by symmetry and by thinking about fractions. So let me just let me put that away for a little bit and let's take a look at the rest of this problem. Letter B. For each additional terminal ray, state the angle based on symmetry in both degrees and radians. All right, so I'd like to point something out about the unit circle before we get too far into this. The unit circle is based on multiples of these angles. All right, multiples of 30 degrees, multiples of 60 degrees, multiples of 45 degrees, even multiples of 90 degrees. And some of those are, of course, multiples of each other. So here's what I mean. Let's just for a moment, over on the side of the paper over here, let's just think about this, right? Let's talk about multiples of 30, right? 30 degrees is pi over 6. 60 degrees, which is 2 times that, would have to be 2 pi over 6, but that reduces to pi over 3. 90 degrees would be 3 pi over 6, but that reduces to pi over 2. Right, think about this for a second. We skipped right over the 45. That makes sense. I've got 30 multiplied by 2, I've got up to 60, multiplied by 3, I've got up to 90. The next one is going to be another 30, right? So if I add 30 to that yet again, I have 120 degrees. That's 1 more pi over 6, that's 4 pi over 6, and that's 2 pi over 3. So this is 120 degrees, which is 2 pi over 3. Now, of course, 2 pi over 3 is, of course, just twice pi over 3, 60 and another 60. So if 60 degrees is pi over 3, then 120 degrees is 2 pi over 3. For a moment, I'm going to be skipping these things because they're the multiples of 45. But if I go another 30 degrees, right, I have 150 degrees. That's 5 pi over 6. Just notice, I'm just going up in pi over 6s. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. And that is 150 degrees. And notice I cannot reduce that. That's 5 pi over 6. Right? So anytime I can reduce these, I will. So 2 pi over 6 3 pi, can be reduced to pi over 3. 3 pi over 6 becomes my 90 degrees pi over 2. 4 pi over 6 reduces to 2 pi over 3. 5 pi over 6 can't be reduced. Now if I add another 30 on there, right, I'm at 180. Right? And 180 degrees now is 6 pi over 6, which is just pi. And we're sitting right here. 180 degrees, which is pi radians. Probably the most important of all in terms of those angles, right? 180 degrees is equal to pi radians. Okay, and I can just keep doing this. In fact, that's going to be the slow way of doing it, Kirk. Let's just lasso these and let's delete them. Remember, we had 180 degrees was equal to 6 pi over 6. If I add another 30, I have 210 degrees, and that's 7 pi over 6. So that's going to be right here. 210 degrees, 7 pi over 6. Let's again jump a little bit further. And let's add another 30 degrees, and that's 240 degrees. And that's going to be 8 pi over 6, but that'll reduce to 4 pi over 3. And that's going to be right here. 240 degrees. Whoops, I hate it when I do that. 240 degrees, and that's going to be 4 pi over 3. Let's add another 30 onto there. That's 270 degrees. That's going to be 9 pi over 6, but that will reduce to 3 pi over 2. And that's our angle right there at the bottom of the unit circle, 270 degrees or 3 pi over 2. All right, coming around, right? Add another 30 degrees, we're up to 300 degrees. Add another pi over 6, and we're at 10 pi over 6. Reduce that down, and we're at 5 pi over 3. Right? Actually, let me get the degree measurement there, sorry. So 300 degrees, which is 5 pi over 3. Just one more of these 30 to add on. Add one more, we have 330 degrees. That's going to be 11 pi over 6, which we cannot reduce. 330 degrees, and that's 11 pi over 6. Whew, wow. Now, by the way, I could add one more, right? That would bring me to 360 degrees, which would also be 12 pi over 6, which would reduce down to 2 pi, a full rotation. Okay? Now, I'd like to point something out really quickly. When we look at the special angles, there's tons of other angles. There's 50 degrees, there's 67 degrees, there's 23 degrees. These are just the ones where we can come up with these really messed up coordinates for. It is what it is. But what I do want to point out is that in each quadrant, there is an irreducible form of each one of these, right? Pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, right? And then we'll eventually get into the pi over 4s in just a moment, right? So let's start doing those now. Let's start taking a look at multiples of 45 degrees, which aren't nearly as fun as multiples of 30. Okay, but keep in mind, right? We have a 45 degree, so we've got 45 degrees, and that's pi over 4. Then when I multiply that by 2, I get 90 degrees, and that's 2 pi over 4. But then that's pi over 2. Now we already have that one labeled. That's just the top of the circle. So let's add another 45 degrees. That's 135 degrees. And that's going to be 3 pi over 4. And that's going to be right here. So that's 135 degrees, 3 pi over 4. Okay, if I add another 45 degrees, I'm at 180. And that's 4 pi over 4. But 4 pi over 4 reduces to pi. Okay, let's get that third quadrant angle. If I add another 45 degrees, I'm at 225 degrees, and that's 5 pi over 4. And that one doesn't reduce, so I'm at 225 degrees, which is 5 pi over 4. Sorry about that getting kind of small. All right, now if I add another 45 degrees, I'm at 270 degrees, which would be 6 pi over 4, which would reduce again to 3 pi over 2, but we already have that one. Now, one more time, if I add another 45 degrees, I've got 315 degrees, and that's going to be 7 pi over 4, and that finally flushes everything out. We've got 315 degrees, and that's 7 pi over 4. And again, notice in each one of the quadrants, we have an irreducible pi over 4. Here it's pi over 4, here it's 3 pi over 4, here it's 5 pi over 4, and here it's 7 pi over 4. And again, keep in mind that a half rotation is pi, right? So this is a quarter of that rotation, 1/4 of a pi. Then there's 1/2 pi, 3/4 of a pi, and a full pi. Then 1 1/4, which is 5/4, 1 1/2, 1 3/4, which is 7/4, and then 8/4, which is the same as 2 pi. Whew, oh my goodness. And all that was just getting the angles laid out. That didn't work. Let's try it again. And let's delete all of those. Okay, so now let's get into some fun symmetry. Letter C. Using symmetry, state the coordinates of each additional terminal angle ray. So now what I want to do is I want to come up with the coordinate pairs for every one of those. And that may seem like a huge task, but it's actually really easy, all right? And here's why. Let's start with the really simple ones, okay? The 180 and the 270. Those are simple because the 180 simply is sitting out here at -1, 0. And the 270 is sitting here at 0, -1. Sorry that I couldn't quite fit it in there down below. Now, those are simple but very important. Let's tackle all of these using these things in terms of symmetry. Here's what I mean. If I take this particular angle at 30 and I reflect it across the y-axis, I'm here at 150, right? So all I have to do is take this coordinate pair and negate the x-coordinate. That's it. So when I do that, I can come over here and say this is at -√3/2, comma, +1/2. So that's at 150. Now, what I'd like you to do is, based on that, I'd like you to fill in the coordinates for 3 pi over 4 and 2 pi over 3. Pause the video now and just use symmetry to do that. Well, 3 pi over 4 is going to be the 45-degree angle, or 45-degree ray reflected across the y-axis. So 3 pi over 4 will have exactly the same coordinates as this one does, but with the x-coordinate negated. So at 3 pi over 4, we're going to have -√2/2, comma, +√2/2. Okay, cannot get rid of that line. There it goes. All right, and likewise, 2 pi over 3 is going to be the reflection of pi over 3 across the y-axis. So I'm going to take 1/2, comma, √3/2. I'm going to negate the 1/2, and it's going to be -1/2, comma, +√3/2. Just the symmetry, right? That's the beautiful thing about circles, is that they're symmetric. And I bet you can now see how this goes. We can now find all of these coordinates by taking these and reflecting them across the x-axis. For example, 7 pi over 6 will be 5 pi over 6 reflected across the x-axis, which won't change the x-coordinate, but will negate the y-coordinate, right? So this now is just this one reflected across the x-axis. Why don't you go ahead and fill out the coordinates then for 5 pi over 4 and 4 pi over 3, obviously 225 degrees and 240 degrees. All right, hard to see this all on the screen at the same time, but, right, for 5 pi over 4, there we go. For 5 pi over 4, we're going to take the coordinate pair at 3 pi over 4. We're going to reflect it across the y-axis. That's going to leave the x-coordinate unchanged and negate the y-coordinate. So 5 pi over 4 will be -√2/2, -√2/2. Bring that a little bit closer. And the 4 pi over 3 is going to be the 2 pi over 3 reflected across the y-axis. So the negative 1/2 is going to stay as is, and the root 3 over 2 is suddenly going to become negative. So come down here, barely fits it in now. That's going to be negative 1/2, comma, negative root 3 over 2. Notice that in the third quadrant, right, both the x and the y coordinates are negative. In the second quadrant, obviously, the x coordinate is negative, but the y coordinate is positive. In the fourth quadrant, both are in the first quadrant, both are positive. Now what I'd like you to do is fill in all the coordinate pairs for those 3 remaining angles in the fourth quadrant. Pause the video now and go ahead and do that. All right, well, 11 pi over 6 is going to be the reflection of pi over 6 across the x-axis. That's going to leave the x-coordinate the same and negate the y-coordinate. So this is going to be root 3 over 2, comma, negative 1/2. 7 pi over 4 is going to take pi over 4 and do the same thing. Root 2 over 2 is going to stay positive, and the y-coordinate is going to become negative. And 5 pi over 3 is going to be the same as pi over 3 reflected across. So we're going to have 1/2, comma, negative root 3 over 2. Again, what you might notice, and I certainly hope you do notice, and this is especially nice when you think about radians, is if you look, and let me do a particular different color. Well, what will work? Black, I guess. We don't want to go with green, I know that. Let's say I took pi over 3. And I circled every version of pi over 3 on here that was irreducible, right? If I looked at all the angles, right, and that is literally 1 pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, notice that their coordinate pairs are identical except for the sign change. 1/2 root 3 over 2, negative 1/2 root 3 over 2. This one you can't see. Negative 1/2, negative root 3 over 2, and positive 1/2, negative root 3 over 2. Right? They're all the same coordinate pair, but just negated or made positive depending on what quadrant they're in. And the same is true for all the irreducible pi over 6s, all their irreducible pi over 4s. So how does it look in sort of its glory? There it is, right? Tiny, even on the big screen, in order to get it all to fit, but all there. The most important 4 pairs, right? 1, 0, 0, 1, negative 1, 0, and 0, negative 1 at 0, 90, 180, 270, or 0, pi over 2, pi, and 3 pi over 2. Now, those are simply the angles between 0 and 360 in the counterclockwise direction. But as we saw in our first lesson in this unit, right, we can have other angles. We can have angles that are negative. We can have angles that are bigger than 360. We can have other angles in radians. So let's take a look at exercise number 5. For each of the following angles drawn in standard position, give the coordinate pair from the unit circle. So, negative 120, right? How do I want to get the coordinate pair that's at negative 120? Well, I need to think about the angle that's on this unit circle that is coterminal with this. Now, one way to do that is to sort of draw out a rotation diagram. Go like this, right? 120 degrees counterclockwise. And then I want to think about what this is clockwise. Right? Now again, they're not the same rotation, but they end up in the same place on the unit circle, and that's 240 degrees. So now I go to my unit circle, I go to 240 degrees, which is also the same as 4 pi over 3 radians, and I see the coordinate pair negative 1/2, comma, negative root 3 over 2. And that's my answer for letter A. All right? So, what I'd like you to do in letter B is think about 495 degrees. See what angle on the unit circle is coterminal with 495 degrees, and then give that particular coordinate pair. Pause the video now and go ahead and do that. Well, keep in mind what 495 degrees means is that we've gone around the circle one complete rotation, which takes 360 degrees up, and then some additional rotation. So one way to think about this is I can subtract 360 degrees, and I will get 135 degrees. So this is coterminal with 135 degrees, which means it's right here. Now again, keep in mind what I've really done is I've done this, but that doesn't matter, right? I've ended up at 135 degrees, which means my coordinate pair is negative root 2 over 2, comma, root 2 over 2. Okay, now let's work a little bit with radians. Let me erase, right? Letter C, negative pi over 3. Awesome. Well, negative pi over 3, right, just means that we're moving clockwise by pi over 3 radians. Now here is counterclockwise by pi over 3 radians, right? So this is positive pi over 3, which means that negative pi over 3 is going to be coterminal with 5 pi over 3. In which case the coordinate pair is 1/2, comma, negative root 3 over 2. All right, see if you can think about 5 pi over 2. And feel free to think about it any way you want. Maybe you want to convert it first to degrees and then do something like letter B. Maybe you can think about how many pi over 2's it is, right? See what you can do and then try to figure out what the coordinate pair is. All right, so again, one way is to convert it to degrees. If you went like that, you might have said, well, 5 pi over 2 is 5 times 90, which is 450 degrees. And then if you subtracted 360 from that, you'd find it was 90 degrees, in which case the coordinate pair is simple, it's 0, 1. Or another nice way to do it, okay, is that, and this is critical, right? Every quarter turn is a pi over 2. So remember, I'm going to 5 pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. And I'm now back at the top of the circle. That works great because 5 pi over 2 is relatively small. It wouldn't work so great if we were like 113 pi over 2. But we're not going to worry about that so much. Again, that is 5 pi over 2, straight up north. All right, that was a lot, okay? Wow, what a messy lesson, right? But what it really got into was a lot of important things. Number one, this thing we call the unit circle. A circle centered at the origin, whose equation is x squared plus y squared is equal to 1. That's not a piece of trivia, by the way. That's going to be very important throughout this unit, the equation of the unit circle. All right, we then looked at some special angles on the unit circle. All those angles were multiples of 30, 45, 60, and 90. And of course, we also looked at how those angles manifested themselves in the second quadrant, third quadrant, and the fourth quadrant, and how they were also represented in terms of radians. It's really critical for you to start learning that 30 degrees is pi over 6 radians, that 45 degrees is pi over 4 radians, 60 degrees is pi over 3 radians, and really critical, 90 degrees is pi over 2 radians. Those first quadrant angles and their radian equivalents are very, very critical. We saw how we could use symmetry by taking then their coordinate points and reflecting them across the y-axis, the x-axis, or both the y and the x-axis, which by the way means we're reflecting them through the origin, in order to come up with all those coordinate pairs. One last thing I do want to mention, because this can really get lost in the weeds. We look at these special angles, 30, 60, 45, 90, 180, things like that, and their multiples, because we can find their exact coordinates on the unit circle. That's what makes them special. But every angle we could draw a terminal ray on, there would be a coordinate point where that terminal ray hits the unit circle, and that coordinate pair, whatever it was, would satisfy x squared plus y squared equals 1, and will become important for us to understand when we start to look at sine and cosine in the next lesson. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking. and keep solving problems.